Hello. So today we're going to go over momentum, impulse, and conservation of momentum. That's going to be our next unit for Unit 6. So you've probably heard of the word momentum before, and it's pretty close to the definition that you're used to. Impulse might be a little new, and then we'll talk about conservation momentum. So what this unit is it's just going to be a short, like 3-week unit. So before we talked about force that had to do with like mass, acceleration, and we're able to solve where something is versus where it might be going. And then we did an energy analysis where we looked at things like mass, velocity, things still of that nature. So how heavy something is, how much it moves. And that was a second type of analysis. Now here we're going to have a third type of analysis where we're going to use kind of the momentum and the impulse of an object to predict things about it and to describe the change in motion. So the first term is going to be momentum. So this is one of those science terms where we actually, our everyday use of it is pretty close to the physics definition. So momentum is really when there's mass with some motion. So you might see if someone's running and it's hard to stop down, you might say, hey, that person had a lot of momentum. That's because they had mass and a velocity. So in physics terms, the equation for this is P equals mv. P stands for momentum for us. If we remember, M stands for mass. So let's just, so we don't get confused about that. M is mass. So momentum is mass times velocity. The units are a little weird. They match up with the equation, but they're not anything nice like newtons. So the units are kilograms times meters per second. So that's going to be our units here. One big thing is that momentum is a vector quantity. One of our ideas from before was a scalar quantity versus a vector quantity. The big difference was a vector quantity has a direction. So for momentum, when we're doing our equations, the direction is going to matter. So we're going to need to define a positive direction. And then most of them, things are going to be moving in the positive, but you might have things moving in opposite directions in which you would have to have one positive, one negative. So momentum is a vector quantity. That's big. So let's do an example with this equation. So what is the momentum of a 40,000 kilogram train going 2 meters per second? And what is the momentum of a 2,000 kilogram car going 40 meters per second? So we have a heavy train going pretty slow and a heavy car going pretty fast. So let's see how this will look. So let's do the train over on the left. Our equation for momentum was P equals mv. Remember, P is momentum here. So I don't know momentum. I know the mass of the car was 40,000, or the mass of the train. The velocity of the train was 2. And now you can just multiply those together and you get the momentum. And the units were kilograms times meters per second. Moving on to the car, same sort of procedure. You start with your equation and you fill in what's known. So you have P equals mv. So we don't know the momentum. That's okay. We'll leave that in there. The mass of the car was 2,000. The velocity was 40. Now all we got to do is multiply those. Looks like it's going to be the same answer. Yeah. So the momentum was 80,000 kilograms. All right. So now if we want to compare the two, obviously they're the same. So let's start thinking about physically what momentum means. So originally you would think, hey, this train is way heavier. That's going to have more momentum. That's the right idea because more mass means more momentum. But you'll see the car had to be going way faster to have the same amount of momentum just to catch up. So really what you need to know here is you need to know how to use the equation and you need to know how mass and velocity play into momentum. So let's try another one. 1,000-kilogram car accelerates from rest to 30 meters per second. Find the following: initial momentum, final momentum, cars change in momentum. So for initial momentum, we have, I'm going to use some subscripts here. So we have PI for initial. I use initial. We did that with velocity a little bit last time. Equals M times VI. So the initial momentum, if I keep drawing rho, this is the thing for density, by the way. We'll get to that later. All right, PI is equal to the mass, which is 1,000, times initial momentum. The car accelerates from rest to 30 meters per second. So the question is, what's the initial momentum? If it starts from rest, this tells you VI is 0. So that would give me 0 meters per second. And PI would be 0 kilograms meters per second. So that's it for the initial momentum. Final momentum, I'm going to get PI is equal to M, or no, my bad. It's the final. So we're going to get PF is equal to M times VF. And then if we're going to go plug that all in, we get P, the final, the mass is the same. And then the final velocity is, it goes from rest to 30 meters per second. So it's going to be 30. And at that point, it's just algebra, multiply out. You get the final velocity is 30,000 kilogram meters per second. So again, this is pretty straightforward. You just got to know P is momentum, mass, velocity. A few other things you got to know. Rest means 0 meters per second. So now what is the car's change in momentum? We're going to get more into this later in this unit. So change in momentum is just going to mean, let's just talk about notation a little bit. Delta P, remember delta means change in, and what it really means is P final minus P initial. So if I'm just going to use these numbers here, I have 30,000 minus 0. And there we go. Okay. This change in momentum value is going to be very important for us. So one of the ways we analyze momentum is we see how much momentum an object gained or how much momentum an object lost. Eventually, we're going to be able to tie force into that, and you'll see that over the following weeks. But a big thing in physics is how much momentum was gained, how much momentum was lost, and we can quantify that. Okay. The other thing we're learning today is impulse. So what impulse is, it's how long a net force acts on an object. So impulse is a word that's not used as much. So impulse is how long a force acts. So throughout what we've been doing so far, we talked about forces in the force unit where F equals ma. We talked about forces in the work energy theorem where there was force. So there was like F equals ma. We were talking about forces. We had the change in kinetic energy equals F times D, where we talked about forces. But one thing you'll notice, what neither of these have is time in there. So impulse is the physics version of dealing with how long a force is acting. So get rid of that. So impulse is defined as the force times the time that the force was acting. think if you're pushing on a box with 20 newtons of force for 3 seconds versus pushing on a box with 20 newtons of force for 3 minutes, that should have a different effect on the box. Now we're going to see how to play that in. And our impulse equation is that impulse is equal to the force times the time and is also equal to the change of an object's momentum. So this is going to be one of our big ideas here where we get into really want, and we'll talk about this more this week, but one of the big ideas is we're being able to relate force to change in momentum. So we got force, time, mass, velocity all in here. The units for impulse is newtons times seconds. That makes sense because force is newtons, t is seconds. And then, or it's also the same as kilograms meters per second. So these units are equivalent. That's why impulse and momentum can be equal to each other. And real quick, if you want to know why, newtons is in kilograms times meters per second squared. If you multiply that by seconds, one of the s's cancel, you get kilograms meters per second. So you can see how Newton times second is the same as kilogram meters per second. Let's do an example. Or before we get to the example, one of the things we need to cover is force versus time graphs. One of the ways to analyze a situation is you analyze it as time goes on and you see how the force changes on the object. So the big key here is the impulse is equal to the area underneath. So now we've had these types of situations before where we were messing with the area underneath. So this will make more sense when you get into calculus, but anytime you take the area underneath a curve, what you're really doing is multiplying these two axes, force times time. So the area would be force times time, just like before when we had time and velocity and we did the area, it gave us distance. So that's a concept where if you guys want to go into science in college and things like that, knowing these two things, knowing that if you multiply the two axes, or if you take the area underneath, it's the same as multiplying the axes. Pretty much. It's just like a integral, and you don't need to know this for impulse, but if I was to find the slope, that would be like dividing the two. So area would be ft, slope would be f over t. You don't need to worry about that right now. So big key here, if you're tracking the force over an amount of time, the area underneath the curve for a given time is going to give you the impulse. So here, say I would, so yeah, right here, you got the base of this square times the height of this square would give you the impulse from 0 to some time t. Remember, if it's a rectangle, you just have base times height. If it's an area, you have 1/2 base times height. Those are just area equations. It also might be a weird shape where you have to like cut it up like we did before with triangles and rectangles. All right, let's try out the equation. So a ball is stopped by 100 Newton force over a time period of 2 seconds. Determine the impulse. Okay, so here we have impulse is equal to force times time. Impulse, we don't know impulse. Force, we got to remember is in newtons. I should probably write this as a capital F. There we go. And then time was 2 seconds. So the impulse is going to be 200 Newton seconds. So all our units here are staying relatively the same as before. We have force in newtons, time in seconds. We got mass in kilograms. We have velocity in meters per second. So no new units here except for impulse and momentum. And then that's how you would use that equation. So if I was to look at this as a graph, and this was T and this was F, what it would be is from 0 to 2 seconds, there's a constant 100 Newton force. So there's a constant 100 Newton force. And then if I was to take the area underneath here, this would give me my impulse. So you see where you got your base times your height, and that's just an example. So big picture today, momentum, impulse. We had force analysis to study motion. We had energy analysis, and now we have momentum and impulse. We got two new equations, and